All right, we are continuing chapter 10. We are in chapter 10.3 today, and we're going to talk about, now that we're talking about the different phases, we talked about gases in the last chapter, and we're talking about liquids and solids in this chapter. We want to talk about the phase transitions. What are the terms that we give to changes in the phase in that process, and maybe what energy is involved in it. We know that we have to heat things up in order for the phases to change. We have to add energy, and then some key terms that we're looking at with changes in phase. So the first phase transition that we're going to look at is the phase transition between the liquid and the gas. So I'm going to write out, this is going to be a liquid and gas transition. And we have two possible transitions here. One is going from the liquid to the gas, and we call that vaporization. A liquid vaporizes and becomes a gas. And the transition back down from a gas to a liquid is called condensation. Vaporization and condensation, just the terms for transitioning from a liquid to a gas or gas back down to a liquid. And if we have a closed container of a liquid, I'm just going to make it a box. If we have a closed container of maybe water, for instance, there is always some portion, even if it's very small, some portion of that liquid has had enough energy to escape the liquid phase and go into the gas phase. So there's, even if it's just a little bit, at a given temperature, room temperature, there's a little portion of the water that is in the gas phase. We call that vapor, water vapor. So vapor is the portion of the substance in the gas phase. It's going to exist above the liquid phase of that same substance. Okay, so we have a closed container of water. There's some portion of that that's in the gas phase. We call that the vapor. And the vapor pressure is the pressure caused by that vapor portion. Okay. So there is some portion in the gas phase, and in a closed container of a liquid, there is an equilibrium between vaporization and condensation processes. Okay, that's what causes the vapor to exist. There's a little bit that's able to come back up into the gas phase, and at a given point in time, right, one of these may drop back down into the liquid, and there may be a particle in the liquid that's able to jump out into the gas phase. And so there's some equilibrium here where particles are switching phases, but the amount still remains pretty small that's in the gas phase. At this point, there is a pressure exerted by that portion in the gas phase, and that's what we call the vapor pressure. The vapor pressure is the pressure exerted by the vapor particles. Okay. And it may be very low. If there's just a little bit, a small portion of gas particles, then when they hit the container walls, it's a very low pressure versus the pressure that may exist when there's a lot of vapor in that container. So the vapor pressure of a substance is going to depend on the strength of the intermolecular forces. So if we're imagining some substance, if the intermolecular forces are strong, then it's going to be difficult for particles to escape the liquid and go into the gas phase. So if IMFs are strong, it's more difficult for particles to escape the liquid phase. And that escape is necessary for it to go into the gas phase. So with stronger IMFs, we're going to see fewer particles in the gas phase or in the vapor, right? Fewer particles part of that vapor, and so we're going to see a lower vapor pressure. More particles are going to mean a higher pressure, and so if the IMFs are strong and there are fewer particles in the gas phase, then we are going to see a lower vapor pressure. Okay. The other thing that it depends on, vapor pressure, is temperature. What if I have this closed container of water and I heat the water up? If I heat up the water, then more particles have a higher energy. We're increasing the energy of the particles. So if temperature is increasing, then liquid particles have a higher kinetic energy. And they're going to have more of them are going to have enough energy to escape into the gas phase. More particles will have enough energy to escape into the gas phase. Okay. All it takes is some amount of energy to overcome that intermolecular force. And if we increase the energy of the particles, then more of them will have that ability to escape and to break the intermolecular forces. So we're going to see with higher temperature, with increasing temperature, we're going to see a higher vapor pressure. Okay. Increasing temperature is going to mean a higher vapor pressure, more particles in the gas phase. Okay. So far, this is still all conceptual, right? You just got to think about what these things are and imagine things at the molecular level. The other point, the other kind of characteristic that's important to this this vaporization and condensation process, the transition between gas and liquid phase, is the boiling point. And if we think about it, we can think about the boiling point of water. That's this point where the water starts to vaporize pretty rapidly, right? We start to see more particles in the gas phase. That's going to be a higher vapor pressure. And the technical definition of a boiling point is the temperature. And like for water, it's 100 degrees Celsius. At that temperature, the vapor pressure of the liquid is equal to atmospheric pressure. And it's the atmospheric pressure wherever you are. So boiling point can change depending on atmospheric pressure. It can change just a little bit, but maybe imagine being in the mountains. The atmospheric pressure is a little bit lower, and so the boiling point can lower a little bit because that atmospheric pressure is a little bit lower. It takes less energy to get the vapor pressure up that high. But it's a temperature where we're starting to break the intermolecular forces. It's very easy to break the intermolecular forces, and we have enough vapor where that vapor pressure is equal to atmospheric pressure. This also will depend on the strength of intermolecular forces. If you have, because we said vapor pressure depends on it. So if we have weak intermolecular forces, the boiling point can be very low, where it's very easy to get enough particles into the gas phase to equal atmospheric pressure. If we have something like water where the intermolecular force is strong, then it takes a lot of energy. It takes a higher temperature to get enough gas particles into the vapor, right, into the gas phase, where enough liquid particles into the gas phase, I guess, where that vapor pressure is equal to the atmospheric pressure. Okay. So boiling point will depend on the strength of the intermolecular forces. The amount of energy involved, so there's some amount of energy, and we see that with water. We have to heat up water to get it to change phase from liquid to gas. And the amount of energy has a specific term to it. It's called the heat of vaporization. This is going to be the energy required to vaporize a liquid. And I'll say it's the energy change associated with vaporization. There's some increase in energy associated with vaporizing, and that can depend on the substance, right? If it takes more energy to vaporize something, then that means we have a stronger intermolecular force. But for water, we'll look at this example for water. All right, I'm just going to continue. For water, we are looking at the transition, so H2O liquid to H2O gas. The energy associated, heat of vaporization, has an interesting term given to it. And the term is this delta H, triangle H. And that's going to mean change in energy H is going to represent the energy. Okay. And for water, this is going to be 44.01 kilojoules per mole. Okay. 44.01 kilojoules per mole. What that means is for a mole of water to transition from the liquid phase to the gas phase, it's going to require 44.01 kilojoules. That's a quantity of energy. Okay. What we see is this is going to be a positive value. And what that means is energy is required for this transition. This is going to be an endothermic process. Vaporization requires energy. Okay. It's going to have a positive delta H value, positive change in energy, because energy is increasing. It's required for this process to go. Positive delta H value. And we say that it is endothermic. Okay, that means it requires energy. It's the same thing. The definition of endothermic is just that guy. Okay. If we look at the reverse process, if I were to consider the opposite, condensation, we see a little bit of a change in how we describe that. So if we do the opposite process, and maybe I look at for condensation, we see that everything kind of becomes opposite. For condensation, delta H, the change in energy, is going to be a negative value. That's going to mean energy is being removed. Everything's being cooled down. Maybe, right, if we cool a gas down, it'll become a liquid again. It's going to remove that much energy from the gas. So we're going to see a negative value. Because energy is removed. And that's going to mean it's an exothermic process. Heat is coming out of the system. Energy is being removed from the water vapor in order to make it a liquid. And we're going to see that as a negative sign. It's the same amount of energy involved. That the amount of energy required to heat the substance up to a gas is the same amount that needs to be removed when we go backwards to become a liquid. Okay, so the amount of energy is the same, just in vaporization, it's a positive amount of energy. We have to put the energy in. For condensation, it's a negative amount of energy because we're taking the energy out of the system. Okay. So given that, we're going to look at this value, we're going to do an example, and we're going to see how much heat is required to evaporate 1.5 liters of water. If we have some amount of water, and I'm going to write the heat required up here again, it's 44.01 kilojoules per mole. Or actually, I have it here. It's at a different temperature, so it's a little bit different value. Okay, how much heat is required to evaporate 1.5 liters of water, which is 1.5 kilograms, at, this is kind of a higher temperature, so that's why it's changed, 37 degrees Celsius, and the heat of vaporization is provided here, 43.46 kilojoules per mole. So a little bit less energy required at the higher temperature. So what we're going to look at is we've got some amount of energy. The delta H value for vaporization, they have that subscript VAP for vaporization. That value is 43.46 kilojoules per mole of water. Okay. So it's only that amount of energy for a mole of water. For a different amount of water, it's going to take a different amount of energy. So if we're starting with 1.5 kilograms of water, I need first to convert kilograms into moles. I need to know how many moles of water I have first. So in order to do that, I'm going to first convert to grams. So 1 kilogram is equal to 1,000 grams. And then we convert into moles of water, and moles is, the molar mass says that there is 18.02 grams of water in 1 mole. I just added up the molar mass. Okay. So at this point, I have found moles of water. And now I can use the relationship that tells me per mole of water how much energy is required. And so I'm just going to add that in as a a third conversion factor, where I have per 1 mole of water, I need 43.46 kilojoules of energy put in order to vaporize it. So my heat of vaporization goes in as a conversion factor. And when I do this, I'm going to run the calculation through. I get, let's see, 1.5 times 1,000 divided by 18.02 times 43.46. And let me double check my work. So I'm going to look for 2 significant figures, and I get 3.6 times 10 to the third kilojoules. I put it into scientific notation. I have 2 significant figures, and I put it into scientific notation, but you could also write, it'd be the same answer if you wrote 3,600 kilojoules required. Okay, as long as it had 2 significant figures. And so what this is saying is we have a lot more than a mole of water, so it's going to take a lot more energy in order to vaporize that sample. In fact, it's going to take 3,600 kilojoules to vaporize 1.5 kilograms of water. Okay. So that's kind of the liquid to gas phase transition. I'm going to back up a little bit and then come back. We're looking at vapor pressure being the pressure of whatever's in the gas phase above a liquid. There's naturally some portion that's in the gas phase, and that depends on what the temperature is. If it's a high temperature, then there's a lot in the gas phase, right? Or if the intermolecular forces are weak, then there's a lot in the gas phase. And then once we get the vapor pressure enough energy in where we've reached a temperature where the vapor pressure is equal to atmospheric pressure, we call that the boiling point. And then there's some energy required in order to vaporize a sample, in order to transition a liquid to a gas. And that will depend on the identity of the substance. And it depends mainly on the strength of intermolecular forces. If we have stronger forces, more energy is required. And we said since we say that energy is required, it's a positive energy value. Doing the opposite process, we have the same amount of energy, but that amount of energy is removed from the gas, and we indicate that by a negative sign on the energy change, the heat, for the condensation value. Okay. The other transition that we're going to focus on just a little bit less is melting and freezing, and that's going to be the transition between a liquid and a solid, right? So we have a solid and a liquid, and that transition, right, if we go from liquid to solid, we call that freezing. And if we go from a solid down to a liquid, we're going to call that melting. Right? And the melting point is also a temperature. It's a temperature where we have a liquid and solid in equilibrium. We have both the liquid and solid phases present at that temperature. The temperature at which the solid and liquid phases are at equilibrium with each other, are both present at the same time. Mm-hmm. The energy, I might call this a heat of fusion, the energy required with melting this one has a couple of new terms in it. Enthalpy is another word for like heat or energy. So heat of fusion, it's going to be the energy required to melt a solid. Okay, melting a solid, and we label that delta H fusion or FUS. Mm-hmm. And it's going to be similar to the heat of vaporization. It's just a different transition. Instead of going from liquid to gas, it's going from solid to liquid, but it's the same idea. How much energy is required to melt something? We have to add energy to melt a solid. And this also is going to depend on the strength of intermolecular forces. So this is the energy change associated with melting. I might even write it that way. The energy change associated with the melting process. Okay. And we'll look at this for water as well. So for water, if we're looking at melting, that's going to be H2O solid to H2O liquid. And the energy change associated with that is going to be a little bit less energy than vaporization. So 6.01 kilojoules per mole. Mm-hmm. This is still a positive value. Energy is required. And if energy is required, we call that endothermic. Okay? Energy is required for that process to happen. And we're going to see something similar when we switch the processes as we did earlier. If I instead look at maybe what's the opposite transition, the transition from a liquid back to a solid, that's like freezing liquid water. We have to remove energy from the system in order for it to be able, from that liquid, we have to remove energy for it to solidify. And so that delta H is going to be negative. We have to remove the energy. So negative 601 kilojoules per mole. We have to remove that same amount of energy in order for it to go back down to a solid. And so here we have a negative value. That's going to mean energy removed. Right? Energy is given off by the liquid water, and so we call that exothermic. We have to remove energy in order for the liquid to become a solid. And there may be some questions on the homework asked. You may need to do a calculation, but it would be identical in form to the one we did above, maybe asking how much energy is required to melt a certain amount of ice, right? You would have a mass that we would need to turn into moles because our value for the heat required is in kilojoules per mole. So you'll just always need to make sure the amount that you have of some substance is turned into moles first if it's not already provided in moles. Okay. So mathematically, we would use that the same way. And then the last transition that's less common, but we are going to talk about it, the last transition is sublimation and deposition. And this is actually a transition between a solid phase directly to a gas phase. Solid directly to gas. And so the solid to gas transition is sublimation. If something sublimes, a solid turns directly into a gas. That might be like dry ice, right? We don't see liquid when that happens. And then the gas to solid phase is called deposition. And we see that with water when it becomes frost. So water goes directly and then touches something cold and instantly solidifies. So, gaseous water or like water vapor directly to a solid. Just an idea of what we see overall is if we look at some amount of energy, like we have some axis, and we're looking at these phases, we have solid down here, we have liquid here, and then we have a gas up here. What we've talked about with energy being this delta H value is that the transition from solid to liquid is given, that amount of energy is given by the delta H fusion, the melting process. The energy required to go from a liquid to a gas is usually more energy because we are entirely breaking any intermolecular forces that exist. This is the delta H vaporization. And then if you see the directly solid to gas, the sublimation process, we would have that as delta H sublimation. And all of those increases in energy, this is energy, all of those increases would be presented as a positive value. Their energy is required, and so it is endothermic. It's an endothermic process. If you do the reverse, right, if you start at a gas and come back down, then you just need to change the sign of that energy value. If we go from gas down to liquid, we just change the sign of the vaporization value. If you go from a liquid down to a solid, you change the sign of the fusion value. But the amount of energy, right, is going to be the same. The amount of energy required for this transition is the same. It just depends on which direction are you going. Is energy required as we go up, or is energy released as we come back down? Okay. So this is our phase transition section. This is the end of this particular video. We're going to talk about some heating and cooling curves next, where we start to look at energy required in some of these processes. And we look at kind of where boiling points are positioned and melting points are positioned. So it's going to kind of continue on phase transitions, but a different way to look at it. And then after that, we're going to wrap up chapter 10. So I'll see you guys in the next one.